who is going to be presented by Ramon. Ramon Faganello works in Mercado Libre, in the shipping optimization team, and he obtained his master's degree from the Universidad de São Paulo and his PhD from the Universidad de Campinas. Okay. And well, Mercado Libre is one of the largest companies in Latin America, and Ramon is going to talk about Mercado Libre, so I will not spoil that. I will let him talk about the company, and he's going to present his work, which is a stochastic programming approach for the operational fleet composition problem. Okay, so let's give him a warm welcome. Okay, thank you.
Good evening to everyone. My name is Ramon. I'm part of the Shipping Operations Research Team of the Mercado Libre. Sorry. Do you listen to me now? Sorry. Well, my name is Ramon. I'm part of the Shipping Operations Research Team of Mercado Libre, more specifically of the Shipping Optimization Team. I will tell something about our team structure. It's a great pleasure to be here. We will talk about an applied problem, an applied stochastic programming problem that arises in our logistic network. And before to talk about this problem, I would like to talk some things about Mercado Libre and also about our team. So, Mercado Libre, or MELI, like we say, is the largest e-commerce company in Latin America. Just to give you some numbers, we are present in 18 countries. We have 140 million of users. We also are the most visited retail website in Latin America and have more than 30,000 people working in this initiative. So, finally, we are one of the best places to work in the world. So, it's a very huge company, and our main focus is to provide technological solutions to support the e-commerce activities and also the mobile payments services, something like that. And to enable it, the MELI ecosystem is composed by two main parts. The first one is Mercado Libre, but we also have Mercado Pago, that is like a fintech platform devoted to payment and credit solutions. So, when we talk about Mercado Libre, we are not just a marketplace, but we have another business inside Mercado Libre. We have, for example, Mercado Ads, that is specialized in advertising. We also have Mercado Shops, that is some kind of online store solution to our customers, and Mercado Envios. And Mercado Envios is very important to us because our optimization team is devoted to improve the logistic network that Mercado Envios provides to our customers. Just to give you some dimension of Mercado Envios, in the last finished quarter of this year, in other words, in the third quarter of 2022, we delivered more than 276 million of items by means of our logistic network. So it's a huge volume. It represents almost 92% of all the items sold in Mercado Libre. So it's a very important operation. And to make it efficient, we have our shipping operations research team. Here's a picture of our team. It's a huge team now, but it's relatively new because this team started in 2019 with just 4 people. And now, some years later, we are 84 people. So it's a great team of operations research. We are composed by different background people. So we have engineers, mathematicians, computer scientists. We have people with master's degrees, with PhDs. And we are divided in 2 main parts. The first one, SOT, or Shipping Optimization Team, are people more devoted to optimization tasks, mathematical programming, meteoristics, but we also have the SPF team, shipping probabilistic forecasting that are composed by predictive analytic people devoted to give us good forecasts. And we work together to deliver value to our customers. So, here is our problem. It's a fleet composition problem that arises in the line haul. But what's the line haul? To deliver our items to our final customers, we have a logistic network, like I said. Mercado Envios has this network, and this network is composed by three main parts. The first one, the first mile, connects our sellers to the first mile facility in which the package enters. So, this first part of the process is called first mile. We also have, on the other hand, the last mile that connects the last mile facility inside our net, our ML net, to the buyers. It's the last mile operation. And between this part, we have the middle mile, the focus of the line haul. And here, our mission is to optimize the fleet composition inside all these roads, connecting fulfillment centers, cross-dockings, and service centers. To do that, we have two main models. The Melier is the first one. It can be made by means of dedicated planes and also by means of commercial flights. Meli can hire part of the capacity of commercial flights too. And the main part of our volume is transported by means of the ground model. And in terms of ground model, we have two main hiring modes, I can say something like that. We have the dedicated fleet. Dedicated fleet is some kind of hiring mode in which we hire the full capacity of a truck in a monthly basis. And this truck performs predefined routes at a weekly basis. It has the advantage of present lower costs, but it is less flexible too. Once I hire a vehicle, I have to pay its cost until the end of the month. A more flexible way to hire the vehicles is the full truck load or the spot contratation, the spot hiring, sorry. The spot hirings or the full truck load are the main part of our volume inside the ground model. And basically, it consists about this kind of problem. I think that the image can bring you the idea. So here we have specified travels, and when I say about a travel, I'm saying that we already have a road, a weekday, and a predefined hour in which the vehicle will depart. So we have specified travels, and for each travel, I have to define the fleet size and mix to satisfy the demand of this travel. Basically, our decision here is to provide the best fleet composition, the minimum cost fleet to support this travel. The main idea of our problem is that, to give you some business context, we started by optimizing this kind of problem in Brazil. The people of operations in Brazil already were used to optimize this kind of decisions, but in a simpler way. They had some kind of Excel-based solver, a deterministic one, that can handle a given forecast and the possible vehicles to a given travel. So it considers the vehicle capacities, their fixed costs, and based on this kind of parameters, it can give us the minimum cost solution, some kind of relatively simple optimization problem. But as a usual problem here in this kind of approach is that we have a lot of demand and uncertainty. So the forecast errors sometimes generate a lot of losses in this kind of approach. I will show some small example just to give you some idea. So imagine this travel is a real travel of our Melinet. If I have a forecast of 40 pallets for this travel, and imagine also that this demand of this forecast or this demand of this travel can be satisfied by means of 5 kinds of vehicles, 5 types. I have a bigger one, like a semi-trailer, that can bring 28 pallets, but is more expensive. I have medium ones, like a rigid heavy, or a rigid medium, a rigid light, and I have a smaller one, that is the light commercial vehicle, that is smaller and cheaper. A deterministic solver, like that the operation we're used to apply, can easily give us the optimal solution, the minimum cost solution to satisfy this forecast of 40 pallets. It's not a so complex problem. The optimum cost in this case is 1,814. But in real life, our forecast is not so accurate. So if just one more pallet came in the real life, compared with our forecast, our original forecast, what MEL has to do in this kind of situation to not delay our deliveries is to hire extra vehicles. And whenever we hire extra vehicles, we have increased costs because they are like hired in a more emergency way. So they are more expensive. And our planned cost that was 1,800 becomes 2,300. If you have some kind of more robust solver, a smarter one, that can predict this kind of situation, I will avoid this kind of things, and I can, for example, propose an original planned fleet with a semi-trailer and a heavy. And the final cost would be something like 1,900. In other words, a cost reduction of 15%. So the main idea here is to provide a more robust solution to the operation. Just to give you some literature context also, not only the business one, this kind of problem is called fleet composition problem. Its study started like in 1959 with this paper of Kirby. Is your fleet the right size? It's a simpler version of this problem because it deals with a homogeneous fleet. And 10 years later, the heterogeneous fleet was applied in this kind of problem. And the fleet composition problem, the FCP, is some kind of natural extension of the SCP, the fleet sizing problem. And is our basic problem here. After that, a lot of papers, a lot of research has been conducted about this topic. We also have some streams of research that combine the fleet composition of the fleet sizing problem with another important decisions like the vehicle routing problem. In terms of heterogeneous vehicle routing, we have a lot of research that consider some kind of combination. And we also have the combination of SCP or FFSP with the vehicle allocation problem. And the two main approaches used in this kind of problem are or cream models or time-space models. But if we examine this kind of literature, by investigating it, it's very difficult to find these two attributes simultaneously in the same study. So usually these problems are strategic, dealing with long-term horizons. And here, our problem occurs in a weekly basis. I always need to plan the fleet of the next week. It's a short-term problem, a more operational one. And I have stochastic demands. Usually the demands are deterministic in the literature. Of course, we have exceptions. But I believe the first bullet point here, these two papers, that are papers more related with the stochastic programming literature and present instances that are very close to these two attributes, but it's still not our problem because it's not a canonical FCP problem. It's like a combination of the FCP, an hybrid model, with a vehicle allocation problem, like the other papers I showed in the last slide. So we believe that we are studying for the first time the combination of these two attributes in a more canonical problem of FCP. The second bullet point here has some example of papers, but these papers deals with the attribute 2, stochastic demands, but not with short-term time horizons. So our problem here is twofold. On the one hand, I want to improve my forecast process because it's a real problem to the operation, but I also want to cover this gap by proposing a new mathematical model that can handle the uncertainty in the context of fleet composition in the short term. To do that, we have two streams of work here. First of all, the SPF team helped us to improve our forecast, and after that, we also proposed a novel model, the OFCPSG, Operational Fleet Composition Problem with Stochastic Demands, to address the problem of getting more reliable solutions. So the full process is composed by 3 parts. Between the SPF team part and the hours, we have here some intermediary tasks of data manipulation that is performed by information technology team inside MELI. So the first part, the SPF1, started by replacing the former methodology of forecasting. So SPF team started by evaluating several possibilities, assessing several possibilities to perform a better forecasting process. They analyzed, for example, methodologies like exponential smoothing, long short-term memory, and the others. Their final conclusion was that to use Prophet, that is an open source solution available in R and also in Python, it's some kind of solution developed by Facebook. And it has the advantage of not demand so hyperparameters to be adjusted, and is also possible to apply it in large scale. So given these advantages, the SPF team decided to use the Prophet. Just to give you some idea on how Prophet works, basically it decomposes the forecast in 3 main parts, in a trend one, a seasonality one, and also it considers also the holidays. And it can make available also the possibility of the user input extra regressors in the forecasting process. To make possible the use of the Prophet, the SPF team collected data from 2019 to nowadays. I'm telling something about 3,500 time series. And also they have data of campaigns and holidays. So it's not a so quick process to generate the forecast. It takes like 6 hours. But it was very interesting when compared to the former methodology. Before to enter in the optimization part, it's also important note that Prophet has another nice property here. Maybe it's not so clear now because I'm telling something about demand scenarios. I'm not entering in our formulation at this part. But basically, Prophet has some kind of Markov chain Monte Carlo implemented. So it's possible to extract the demand scenarios and not only a scalar value of demand of this prediction. So it's very useful in the concept of stochastic optimization under the perspective of sampling procedures, like I will show you. And after SPF team finishes its part, what we will have is basically something like that. I have, thinking about the MeliNet, I have for each origin and destination a forecast in terms of volume of packages per day. And what I need to have inside the solver, inside the mathematical model, is something like this. I need a volume in pallets, already converted in pallets, per travel. So a travel is a combination of road, day, and hour. And to do that, the IT team has a script called demand calculator that combines the forecast that comes from SPF team with a lot of data collected inside of our systems, They make possible the conversion of the volume in packages to pallets. They also can find the lane, the transport lane associated with origin and destination, and project the demand in the travels to make the optimization possible. And then the optimization part starts. Basically, to address this kind of problem, we propose a two-stage stochastic programming formulation with recurse. To do that, I need to define two moments in time. I have the first stage, here and now. On the other hand, before to know the real demand, I have to make a plan to the next week. It's our first stage. I have to plan the fleet to the next week. But in the next week, I will know the real values of the demand. So when it happens, I have some possible situations. My plan can be good, but can be not. We saw in the former example, some slides ago, that if I planned less vehicles than I really need, I have to hire extra vehicles. But it's also possible that my plan was some kind of overestimated, and in this kind of situation, I can cancel some vehicles, I can make vehicle cancellations, and when it happens, basically, I do not have to pay the full cost of the vehicle. I have to pay only just kind of penalty because I reserved the capacity of the vehicle, but a restitution arises here when compared with the original vehicle cost. So I have these two kinds of adjustments possible at the second stage. Mathematically, to reach this formulation, we have to define some sets. I have a set of travels. I also have a set of vehicle types. And for each travel and vehicle type, I have set V of individual vehicles. We also have here some data coming from the dedicated fleet. So like I said, it's another hiring mode inside the line haul to ground vehicles. But here, they are just parameters to us. We know exactly, in each travel, the number of dedicated vehicles and also their capacity. It's just input data here. We also have the capacities of the different types of vehicles, the costs associated with each type to each travel, and we have the stochastic demands. So at the first stage, we have here binary decision variables. So for each travel and each vehicle, if this vehicle is assigned to that travel, this variable receives the value 1 and 0 otherwise. My formulation is given by these four expressions. The first one is the objective function. I will explain it better. The second one is a relatively simple constraint that it says that for each travel, I must have at least one vehicle planned, dedicated or full truck load or spot. In 3, I have some kind of symmetry breaking constraints, classical ones, and in 4, I have the domain of the decision variables. Note that my objective function is composed by the minimization of the originally planned vehicles and the expected value of the second stage function Q. And this function Q is defined given a value of the vector x, in other words, the solution of the first stage, and given my possible demand realizations. So before to show you how to calculate this function Q, we have to define some extra parameters and variables. We have here the alpha parameter that says that for each type of vehicle K and for each travel T, I have a cost of extra vehicles. Beta is very similar, but related with the restitution values for each vehicle when I have a cancellation. And I also have here the parameter theta. This kind of parameter is like a risk-averse parameter. It controls the number of pallets that will be transported by means of extra vehicles in a given optimization process. I think it will be more clear inside the model. I also have two types of continuous variables, S and E. They give me the lack and the excess of capacity respectively. And we have here general integer. Note that at the first stage we have binary variables. Here we have general integer variables. For each kind of vehicle and for each travel, I have, so in the variable Z, the number of extra vehicles, and in W, the number of vehicles that are in really canceled. And with these definitions, I can reach the second stage formulation. So the Q function that allows me to calculate the value of the restitutions associated with the second stage for a given first stage solution and for a given demand realization. Note that this function is composed by the sum of the extra vehicles costs and also the restitutions associated with vehicle cancellations. I think that some relevant notes here, or observations here, are the first one. Here, we apply some kind of special word sets of the type 1 to model a relationship between variables S and E. It's important in our formulation. It can be made of other ways, but when using a mathematical programming solver, it can bring better results depending on the solver. So it helps us to get a better performance. And here, the expression, the constraint 9, is the expression that I commented that can help us to understand the theta parameters. So here, I can control the volume of pallets that will be transported by means of extra vehicles. It's like a risk-averse parameter and is optional in our model. This problem is not solvable, so we have to approximate it, and we do it under a sterile sampling perspective. So we will approximate the stochastic demands by means of a set of scenarios. And here, the Markov chain Monte Carlo that I said makes sense, the property capability. So we have a set of scenarios. For each scenario, I have a given probability. And now, my demands are scenario specific, and also my second stage variables are scenario specific. And with these definitions, I can bring here the multi-scenario model, or MSM. Model is given by this set of expressions. My objective function minimizes the costs of the originally planned fleet, plus the adjustments associated with the second stage. But note that now these adjustments are weighted by the scenario probabilities. I have here the constraints of the first stage and the constraints of the second stage, now indexed in small s, that corresponds to each scenario. And also my second stage variables here are indexed by s. To solve it, we do not just call the solver to handle the mathematical model. We have some kind of math heuristic that is used. This math, I will not give too much details now. We can tell it after the presentation if you want. But basically, we have two mechanisms to first stage variables fixation. The first one is based on the idea of the scenario decomposition. We try to find consensus between the solution of individual problems when decomposed per scenario. And we also have an additional strategy based on the reduced costs of the first stage variables when you solve a problem called the expected value problem. Expected value problem is a very simple definition. It's a multi-scenario model that has just one scenario. And this scenario is the expected value of the stochastic parameters. Is composed by the expected values of the stochastic parameters. So when we solve the linear relaxation of this problem, we can get the reduced costs of these variables. And Kreinik in 2018 showed that it can be a use of information to develop some kinds of math heuristics to stochastic problems. And we apply it here too. In terms of computation, our algorithms were coded in Python. We use Cplex to inside our math heuristic, to solve the models inside our math heuristic. And the algorithm runs on AWS. So here we have the characteristics of the instances we use, just to make the information available. And here we have some interesting results. The system is already being used in Brazil. Some characteristics of the weekly plan in Brazil. We have something like 6.5 thousand of travels per week. The transported volume in pallets is something between 60 and 90,000 of pallets. It's a big volume. And we have a weekly cost that ranges between 20 and 35 millions of reais. So it's a very huge value too. In terms of mathematical model, we have here results from week 16 of this year until week 48. That it was like 2 weeks ago. Now we are in the week 50 of 2022. Until this moment, we were working with 20 demand scenarios. Now we increased this number to 40. We have here also some out-of-sample stability examination in like supplementary material if you want to see to justify the choice of scenarios. But with 20 demand scenarios that was used until 2 weeks ago, we have a mathematical model with 1 million of variables, 1 million of constraints, and 100,000 special order sets. We have here, in terms of the composition of these variables, we have like 20% are continuous, 5% are binary, and the remaining ones, 75 are general integer. With the math heuristic, we solved this problem in 20 minutes. And here we also have some results. First of all, I will present a more general result, a result that comes from a backtest. And after that, we will select the subsets of routes, of travels, in which the system is already being used to show you the real gain that we achieved until this moment. So we have data, like I said, between the week 16 of this year and the week 48. So I'm telling about 33 weeks. And what we measure here is basically the comparison between our stochastic solution against a deterministic one. For the people that are used with stochastic programming, it is very near to a VSS evaluation, but it's better because it's a backtest. So when you perform a VSS evaluation, a value of the stochastic solution evaluation, basically we compare the recurse problem, that is the solution of the stochastic model, with the EEV, that is the expected value of using the expected value solution. Basically, what it means, we compare the value of the recurse problem, the stochastic one, with the projection of a deterministic model, the expected value model that I said some slides ago, projected in several scenarios. So it's the EEV. And comparing these two solutions, I can understand how much better is the stochastic model when compared with the deterministic one, with its deterministic counterpart. So here, what we really do is something better, because I have the deterministic plan and the stochastic plan, but I also have the real value of the demand. So I can like call my model, fix the first stage variables by using or a deterministic or a stochastic plan, and understand, by using the real demand values and this fixed plan, the total cost of the model, by calculating the adjustments of the second stage. So with this backtests, we can understand how much better is our model when compared to a deterministic one. And our results are good. We have here a cost reduction of 6.3 million of reais in Brazil, and we also have some interesting operational gains. We reduced the number of extra vehicles hired, and also the number of pallets transported by means of these extra vehicles. It's important because it brings more safety to our operation. And here, our real implementation started in week 31, given the timing of the project. So we have 18 weeks after the system go live. This go live is like stepwise, and nowadays we have 40% of the travels already using the system. We have some data challenges to improve the stacks, like I will show in the next steps. But basically, it's an important number. With 40% of the travels using the system within 18 weeks, we have a real gain to Mercado Libre of 1 billion of reais. Considering this subset of travel, it's a cost reduction of 1.5%, almost 1.6%. It's very expressive. And we also have the nice properties of extra vehicles reduction and volume transported by extra vehicles reduction too. And like our next steps, here is just a picture of our front end. Our main objective here is to reach the 100% of system utilization in Brazil. That is our first country of implementation. To make it possible, we have to handle some data problems associated with some travels. It will improve our full process. And in the part of optimization, we also working to improve our method risk, to make it even quicker. And with this kind of improvement, which will be possible to increase the number of scenarios. In fact, we already increased it to 40 scenarios, and it has a very better out of sample stability, so we are reaching better results also in the part of the optimization. And the remaining effort is also related to data, and we also can develop new features to our end users. It's more operational constraints or things like that. Besides that, we also implementing this system in other countries in which Mercado Libre has a logistic operation. Nowadays, we are very close to start this system in Colombia, and we are already started the work in Mexico. Here in Argentina, we still need to start, but it will be a great opportunity too. And the last point is that we also have to embed another kind of decision inside our model. We are here given the optimal fleet composition in terms of vehicle types and the quantities of each type of vehicle, but we also have to select the provider that will, the carrier, the provider that will send this vehicle to our operation. So we already done this kind of implementation to Colombia. So the model to Colombia is an extension of this model that I showed here that comprises this kind of decision, and we will do it to other countries too. I think that it's all. I have here some reference that we used. And like I said, we also have here some supplementary material to support the answer of any question, but I think we now open to questions. Thank you.
Thank you. Nice presentation. A couple of questions. One is about the promotions. The system, I think, Prophet, you mentioned, is able to forecast promotions. What's the effect on that on your demand? And the second question is about the materialistics. Why did you choose a materialistic instead of a meta-heuristic to solve this problem?
Thank you. Regarding Prophet, I'm not the specialist, but yes, it can take into account the promotions. We have the databases with campaigns, like I said, and these campaigns are just the promotions, so it can handle it. I cannot say the details because, like I said, I'm not the specialist of this part, but it takes it into account. And regarding the math risk, it's because the math risk provides us good results. Our solution is like optimal ones. The distance is very small, and it is faster to implement when compared with a meta risk. And here we are we are working under an environment of quick change, and the times our response needs to be very fast. So given these two attributes, we choose math and risk. So whenever I have to implement a new feature, it's easier to implement it in a model and take into account in my math and risk. If I have a meta heuristic, we also have some kind of meta heuristic implemented in another system. For example, dedicated fit is planned by means of meta heuristics, but it is just because we cannot do any kind good by using a mathematical model, because a mathematical model is a flexible way to do it. If you can do it in a good way by means of mathematical model, it's great, because each new constraint I need, each extension is much more easier to implement in the real life. So it's mainly because of that.
So, thank you very much for the talk, obrigado. And one question, did you try, I just noticed you tried progressive hedging. Did you try some decomposition, like scenario decomposition for your problem? If not, why? And if it didn't work, also why? Thank you.
Yes, we are here in our math heuristic, just to show some context. In our math heuristic, we just apply nowadays the first step of progressive hedging, but the idea is the same. We are not at this moment like giving more steps and updating the penalties and the multipliers because of a time issue, because we are solving the model in 20 minutes. With 40 scenarios, we are now with 50. And it's like the limit. Our idea is to improve the math risk to get like a half hour. That is a good time to the operation. And we can also, it's a possible trial. Besides to invest here in this part of the reduced cost-based risk, we can give here more steps in the progressive hedging. But we tried something like that, but the conversions is not so quick. So with several scenarios, even within a parallel implementation, we want to avoid to spend too much time here. So our idea was to implement a second step in our math risk to fix more variables without giving more steps in progressive hedging. And now we are investing to refine it. But it's also a possibility. Basically, give more steps here in progressive hedging too is a nice opportunity here. The main task here is the processing time. Nowadays, we are performing just one step, and we do not solve the full scenario problem. We have some kind of theorem that allow us to replace the original scenario problem by a simplified one that's very quick to solve. So at this first step, we can do it because it's a single step, and we just want to reach the consensus in a single step, so in individual scenarios without penalties and Lagrangian multipliers, something like that. But it's also a possibility. The timing was the main reason why we decided to do it first, but it's something that we can try to. It's even a good possibility. Thank you.
Congratulations for your talk and for Mercado Libre for establishing this group. My question is about the instances first. Are they available for us, for the academy? The first question. The second one, about is there a program, some kind of program with the academy, university? It's a proposition.
Yes. Regarding the instances, they are not available because they are like sensitive data. But now we are also starting to publish in some papers. So maybe in this process we can like generate instance based on the problem, and maybe within some time we can make some instance available. Not at this moment, but maybe in the future. Regarding the program, eu não, quer falar algo, Dani, a respeito? Que Dani Negrotto pode falar melhor que eu aqui.
We can talk then about that. We are open to collaborate with university. We are starting now a program with DTLR, our first collaboration program, and the idea is to continue with that. Yes.
Great, thank you.
Some more questions?